everyone, welcome back to our seminar. Today, Eero Räty is going to talk about positive discrepancy, maximum cut, and eigenvalues of graphs.
Thank you for the opportunity to speak at your seminar. This is joint work with Sudakov from ETH and István Tomon, who's also here in Umeå. Okay, so just briefly some background on discrepancy. So vaguely speaking, discrepancy kind of measures how much substructures can deviate from the expectation. So the particular discrepancy I'm interested in, or we were interested in, is the discrepancy on the graphs. So in graphs, the discrepancy is defined as the maximum of the number of edges in a subset U minus sort of the expected number of edges we would expect to see in U. So it's P times U choose 2. And then here we don't distinguish between sort of positive and negative discrepancy, so we take the absolute value of it. However, there are sort of many other examples where discrepancy is studied as well. So if you consider a subset of natural numbers, then sort of picking a similar definition of a discrepancy as we use for graphs doesn't really make sense, because, I mean, if you just look at the maximum overall, the subset of B, and what's the A intersection B minus the expectation, then you would obviously pick your B to be A, and that's a kind of a dull definition. So instead, we want to sort of pick a maximum over some sets which have some structure. So then we can just restrict ourselves to arithmetic progressions, and that gives rise to this second example of an AP discrepancy. And that is has a kind of a nice application. So one of the proof of thoughts theorem, for example, that any set of positive density has a 3AP if n is sufficiently large. You can prove it by saying that, okay, if you have a set which wouldn't have a 3AP, then the positive discrepancy is actually quite large. And then you could run a density increment argument to get a contradiction. There are also plenty of examples of discrepancy in sort of geometric combinatorics, which I'm unfortunately not that familiar with, so I didn't pick those as examples. But the last one I'd like to mention is sort of Beck-Fiala theorem type of discrepancy problem. So quite often we have some sets living on the grounds at n, and we want to assign each element a value plus or minus 1, and then within each of these sets we calculate the sum of the entries associated to it. And then there are some theorems regarding that if each I is only the at most t of these sets, then the maximum of these sums xsj's can be quite small. However, this is kind of not really related to what I'm going to talk about today, but kind of demonstrates that various notions of discrepancy are quite rich in combinatorics. Okay, so what I'm going to talk about today is graph discrepancy. So I'm always going to denote the edge density of a graph with P and the average degree by D. If you want to, you can basically assume that all the graphs you're going to see today are D-regular. Essentially, so when we move on to look at a few sort of ideas behind the proofs, it's actually convenient to assume that things are D-regular, so you don't lose too much of intuition by doing so. So for graphs, the first result was proved by Räty and Spencer in 71, who proved that this discrepancy is at most n to the 3 halves when the graph has density half. And then that was later extended by Räty, Goldberg, Bach, and Spencer to sparser graphs as well, so that the discrepancy grows always like root d times n. Both of these are tied for random graphs, and as we will soon see, sort of this root d factor is closely related to the fact that for certain sparse graphs, you sort of expect the eigenvalues to be of that magnitude, or at least. So, okay, so for the ordinary discrepancy, we don't really distinguish whether the number of edges inside of Q is more than the average or whether it's less than the average. And in fact, in both of these proofs, techniques are kind of based on considering some suitable random partition and then doing some clever reordering. So you actually can't conclude anything about one-sided discrepancies, but it's kind of quite natural to ask oneself, could we actually ensure that both of these would be large instead of just one of these being large? And just a simple observation is that if the positive discrepancy of G is the same as the negative discrepancy of G complement, which kind of motivates why we here, when we mention the theorem of Räty, Goldberg, Bach, and Spencer, only talk about graphs which have density at most half. I mean, it's kind of, so as we see, sparse graphs behave in a slightly different way, and I find it more natural to think about, talk about sparse graphs rather than graphs which has density 1 minus little of 1. So that's why it's sort of convenient to make that assumption. Okay, so the first theorem concerning one-sided discrepancy was proved by Alon in 1993. So for d irregular graphs, when d is quite small, so at most n to the 1/9, he proved that basically the random graphs are the best, so they minimize the positive discrepancy. So if you sum over the discrepancies of all the subsets, you get 0. So one might sort of feel like that one of them being large might imply the other being large just because the positives have to cancel out with negatives. Of course, that's a very sort of vague argument because you don't know at all how many of those sets gives you a positive contribution, how many gives you negative contribution. But it's actually, so in 2006, Bolobas and Scott proved a theorem which kind of does the very opposite. So they prove that if one of them is small, then the other one must be large. So the product of them has to be kind of what these guys, Räty and others, proved previously, squared. So not just saying that one of them has to be large, but saying that if one of them is just sort of on the level we expect, so root dn, then the other one has to also be of the same order. Or if one of them is substantially smaller, then the other one has to actually beat this root dn bound. So consequently, we have that both of the discrepancies are at least linear. So one could also prove this with some elementary arguments. And it's also easy to see that they can be linear in N. So for positive discrepancy, Turing graphs give a linear positive discrepancy, and disjoint union of cliques, so their complements give a linear negative discrepancy. So roughly a decade ago, Westergaard asked whether this lower bound could be improved if your graph is sort of sufficiently far away from Turing graph. So more precisely, if so there were kind of two variants of this. So the first one was that if P is at least epsilon away from a Turing density, could we prove that the discrepancy is at least this should be a positive discrepancy here on the last one. So that the positive discrepancy is at least what you see from a random graph, or even there is a more powerful variant of this conjecture that if G is just epsilon n squared away from a Turing graph in cut distance, then is it the case that the positive discrepancy is still of the same order as for a random graph? Okay, so before moving on, stating our results, let's discuss briefly about the two other aspects mentioned at the title. So a MaxCut of a graph is the maximum number of edges in cut. So you fix a partition of the vertices into U and U complement, and you pick the one where there are most number of edges between the two sets. So by standard random argument, we know that there exists a cut with at least half of the edges in it. But we kind of want to take the trivial way, so that's why we consider instead the surplus, which is MaxCut minus this half of the edges. And instead ask how large can the surplus be, because this surplus is, for example, for random graphs, it's again root d times n, so in general, little low number of edges, which makes considering this normalized quantity much more sensible. So studying this MaxCut problem under additional assumptions, like when G is H3, has a quite a long history. So I think it was initiated in the 70s by Räty and Lovas, and there has been some recent development in the area, for example, by Stefan Glog, Oliver Janser, and Benny Sudakov in 23. And how does this relate to discrepancy? Well, it's quite easy to prove that for regular graphs, the negative discrepancy and the surplus are the same up to a constant multiples. It's kind of easy to see that if you have a cut which is kind of large, it has many edges between the two vertex sets. So you sort of know that at least one of the vertex sets must miss some edges, giving you an example of set with large negative discrepancy. The converse is not too much harder, but we'll leave it as an exercise. Then the final topic is the second eigenvalue of graphs. So I'll just let lambda i's denote the eigenvalues of G, and just to remind you, I'm sure because this is an algebraic combinatoric seminar, you all probably know that if G is D regular, then the highest eigenvalue is just D. So concerning the second largest eigenvalue, perhaps the most influential result is the Alon-Boppana theorem, which implies that if G has a diameter D, then provided that the diameter is not 2 or 3, then lambda 2 grows like a constant times root D. So I don't really... we'll show some related results where we don't really care about the constant multiples. So that's not particularly important for our purposes. But the thing that I want to point out that the Alon-Boppana theorem is useful up to when D is some small constant times n to the 1/3. But if d is some large constant times n to the 1/3, then it already could be the case that the diameter is 3, in which case the Alon-Boppana theorem, the main term, is just 0, and we can't conclude anything out of it. So how does this relate to discrepancy? So the expander mixing lemma essentially states that the number of edges in a graph between two sets S and T, which may overlap, is basically going to be the number of edges we expect there to be plus or minus some error term, which is bounded by the maximum of lambda 2 and lambda n. So the variant we sort of want from it is the following, where we only look at the number of edges inside a set, which can be proved by essentially the same method. And this implies that the positive discrepancy is upper bounded by lambda 2 times n, and the negative discrepancy is upper bounded by lambda n times n. As appropriate, I sort of mean absolute value of lambda n instead of lambda n. So sometimes if I say lambda n without mentioning the absolute value, please try to remember that I'm talking more about the magnitude rather than the actual value of it. This is provided that both of them are non-zero, because if they are 0, then this plus d term, which can be n, can mess up things slightly. So recall that the Boloba-Scott theorem stated that the product of positive discrepancy and the negative discrepancy is at least d times n squared. So combining this with the expander mixing lemma, we conclude that lambda 2 times the absolute value of lambda n is always at least constant times the degree of the graph. And this is going to be a quite useful fact, because when we look at some constructions giving us upper bounds for discrepancy, because they arise from algebraic structures, we quite often know what they're, or can compute the eigenvalues effectively, but then calculating the discrepancy could be a bit trickier. But if lambda 2 times lambda n is constant times d, then we know that actually the equality must hold in Boloba-Scott theorem, and hence also in this variant of expander mixing lemma. So in those cases, the discrepancy is actually constrained by the eigenvalues exactly, and not just upper bounded by them. Okay, so let me now state our main result. So our main result is that the conjecture of Weierstrass is slightly incorrect. So when the graph is quite sparse, so up to n to the 2/3, then the random one is indeed best. So this extends the result of Alon, who proved this up to n to the 1/9. However, when d is between n to the 2/3 and n to the 4/5, we proved a lower bound of the form n squared divided by d. So these bounds match up to constants at when d is roughly n to the 2/3. And moreover, for the start of this interval, this bound is actually tight. So between n to the 2/3 and n to the 3/4, the discrepancy quite surprisingly decreases. So I'll show a plot of these bounds to give you some intuition shortly. So then you hopefully get a bit better idea what what these bounds actually give. And then between n to the 4/5 and half minus epsilon n, we get a bound which is d to the 1/4 times n. So the second bound obviously holds, it holds for any d, but when d grows, so for example, becomes linear, it becomes fairly useless because it just gives that lower bound that the discrepancy is at least linear in n, which we already knew by some previous results. But then we get this improved bound for large d. And because complete bipartite graph has average degree half n, we know that something should happen near half. That's going, like, there's no hope that we could extend this range to half n, at least if we don't make any assumption that the graph is sort of in some edit distance sufficiently far away from bipartite graph. So basically our results just stop at 1/2 minus epsilon. Regarding second eigenvalue, we get towards the end slightly better bounds. So I should mention that similar results have been proved quite recently by some others. So so basically we get this root d and n over d in the same intervals, and then instead of d to the 1/4 n, I should also mention there is a hidden log n factor dividing this quantity in the bound, which I removed just to make it a bit more simpler. So we improved that to d to the 1/3 in this final range. And that's based on a slightly different result, which is that lambda 2 is actually in this interval lower bounded by square root of lambda n. So a consequence of Bolobash-Scott theorem and expander mixing lemma states that lambda 2 is at least d divided by lambda n, so it has a inverse dependence. But quite surprisingly, it also has a sort of this kind of positive dependence that it must be always at least constant times square root of lambda n. So this result that lambda 2 is at least square root of lambda n was first proved by Igor Bala in his paper which came as a preprint now 3 years ago. That paper is mostly concerned about certain bounds on equiangular lines, which does some fairly involved matrix projections, which then at the end gives this bound. This is also can be derived from a result of Ferdinand Ehringer, which was published last year. So Igor then made the observation that the lambda 2 has to be at least d to the 1/3. I think the fact this sort of first theorem is not really stated in this form in Ehringer's paper, but it can be very easily deduced from it. And this second one certainly appears in his paper. And his proofs are substantially easier than Igor's ones. So it's basically just some nice manipulations of some matrix equations. Ours are sort of slightly different than Ferdinand Ehringer's. There are a few shortcuts we were able to take, and then we adjusted them to also give these first two bounds. And also regarding tightness, so the first two bounds are again tied up to when d is at most n to the 3/4. But also there are examples of graphs where these some constant times n, which have a second eigenvalue of the order n to the 1/3. And I'll show, after showing the plot of these bounds, I'll talk a bit about these upper bound constructions. So just to illustrate these results, so we first, both the upper and lower bound for lambda2 and the discrepancy grow essentially linearly. So we have this root dn bound going up. Then quite surprisingly, it starts going down and starts going up at some point again, which we don't quite know because our bounds are not tight in this interval. And then all of them drop to 0 near half n. Okay, so few words about these constructions. So the first construction is an algebraic construction of Metz, which is a graph, a strongly regular graph with average, degree n to the 3 quarters, and the second eigenvalue is of the order n divided by d. So here, the product of lambda2 and lambda n is of the order q cubed, which is the same magnitude as the degree of the graph. So by the observation I mentioned earlier, this automatically implies that the positive discrepancy is going to be lambda2 times n, and the negative discrepancy is going to be lambda n times n. So this gives us an example where the positive discrepancy is going to be n squared divided by d. So this only does it for this particle d, but I claim that we have a construction for any smaller d. Well, we can just take a random induced subgraph of this graph. So if we take one with probability p, then n is going to drop to p times n, and d is going to drop to p times d. So the ratio between n and d is going to remain the same. So now, by interlacing that, the second eigenvalue of that induced subgraph cannot be larger than n divided by d. But we also know that n divided by d is a lower bound for it. So we get an example for any d less than this. Of course, at some point, this example is going to be worse than a random graph, but the tipping point occurs at the same places where our lower bound changes from root dn to n over n squared over d or n over d for second eigenvalue. So that's fine. So the other construction I wanted to mention is the one establishing the fact that n to the 1/3 is tight lower bound for the second eigenvalue for when the degree is roughly linear. So if d is n divided by p for some prime p, then a recent construction of David, Husna, Johnson, and Bolhill implies that there is a certain strongly regular graph arising from a partial difference set, which has lambda2 being n to the 1/3. So this was kind of a funny coincidence because we were just putting our paper to the archive. We were slightly annoyed that we didn't have any matching upper bound beyond the previous one mentioned. And then this paper literally came a day before we were intended to submit it. And it was kind of a lucky coincidence, because otherwise we would have maybe some of our conjectures could have been written in a slightly different way, but this at least gave us a convenient reason to believe that this d to the 1/3 should be the correct growth rate on the whole interval. Okay, so having said a few words about our results and upper bound constructions, I'll say a few words about how these lower bounds can be proved. So the lower bounds are proved by considering suitable relaxations of discrepancy. So to get some idea, it's convenient to stare at these four kind of related quantities, which kind of closely resemble what the discrepancy looks like. So it's quite easy to see that if we feed a 0, 1 vector, so an indicator vector of a subset to the top line, the definition coincides with the definition of the positive discrepancy I presented earlier. On the other hand, if we allow these values of xi to be between 0 and 1, and not just in the set 0, 1, so not just either endpoint, but anything between, it's quite easy to see that if we fix all but one of them and vary the last one, then the coefficient of the last one is going to be, so it's going to be linear in the last one, so the maximum is achieved at one of the endpoints. So essentially, this first two modified definitions of the positive discrepancy are the same. So it doesn't matter if we take the maximum over those vectors x which are only 0, 1 valued, or whether we take the maximum over those which have xi's between 0 and 1. Okay, so by similar argument, it doesn't matter whether we choose the coordinates from the set -1 or 1, or from the interval between -1 and 1. So now the question is that why is it the case that it doesn't matter whether we pick the entries from the set 0, 1 or from the set -1, 1? Well, it actually does matter, but it's fine if it only matters up to a constant multiple. And the reason is that if we have a -1, 1 vector, which attains this maximum, we can just pick U to be the set of indices where we get have the value 1. And then the discrepancy of this vector is just going to be the discrepancy of U minus the discrepancy between U and U complement, it's defined as appropriate, plus the discrepancy of U complement. On the other hand, the sum of these three terms is just the discrepancy of the whole vertex set, which is 0. So adding these two together, we see that the discrepancy of a -1, 1 vector is just twice the discrepancy of U plus twice the discrepancy of U complement. So if the so-called -1, 1 discrepancy is large, then either U or U complement must have a large positive discrepancy. And that shows that all of these four are pairwise either equal or, in the worst case, within constant multiple of each other's. So hence we can just pick the last one of them as our new definition of positive discrepancy. And why is this convenient? It's convenient because so-called graph quadratic inequality proved by Alon, Makarishev and Naur in 2006, essentially allows us to change this optimization problem where xi's are chosen between minus and 1 with vectors, so unit vectors, where the product is relaxed to an inner product between bi and bj, with the cost of losing a factor of log n. So now, if we look at our definition of discrepancy, so we are summing over those I and j which are joined by an edge. So x, we have for those pairs we have xi xj term, and then we subtract p times the sum of all the products of xi xj where I is not equal to j. So we could just pick our matrix to be the adjacency matrix of the graph minus p times j minus I, or we could just pick p minus j because the diagonal entries are only going to give us a linear contribution, and because we are aiming for something that grows substantially faster than linear, that's going to be small that we can just ignore it. So, motivated by this example, we defined a discrepancy of a symmetric n times m matrix to be the inner product, sure inner product of x and a minus d divided by n times j. So this is just the proper normalizing factor, basically the p term. And recall that in the graph quadratic inequality, we are, in the second one, we are maximizing this over the pairwise inner product of unit vectors. So we can just pick x to be the gram matrix of these vectors, and that's going to be positive semi-definite with diagonal entries at most 1. So our optimization problem is now to maximize this matrix discrepancy over all positive semi-definite matrices, which has diagonal entries at most 1. And then this p disc of g is going to be a lower bound for positive discrepancy up to this log n factor. So just to get us warmed up, let's see what happens if we plug in matrices which are linear combinations of matrices of the form vi transpose, where vi's are orthonormal set of vectors. So the inner product of matrices x and y is just the sum of xij, yij entries, which is quite convenient to view as a Hadamard product of x and y hit with all 1 vectors. And if vi's are an orthonormal set of vectors, then it's an easy exercise to check that what we get is just the sum of the alpha j, beta j terms. So motivated by this example, it suggests that we should probably pick our matrices x that we feed into this discrepancy function to be linear combinations of matrices of the form vi transpose. So let lambda k be maximal chosen so that it's still a non-negative eigenvalue. And consider matrices x and y, which are basically, we pick all the eigenvectors corresponding to, sorry, I've changed from used to be's, but so we pick all the eigenvectors that correspond to non-negative eigenvalues apart from the first one. So why don't we pick the first one? We don't pick the first one because it's it would be anyway killed by this d over nj term. And then we pick y to be kind of the same, but now we weight each of these matrices with lambda j squared. So it's quite easy to see that this matrix has its diagonal entries at most 1. Why is that the case? It's because each of these matrices is a positive semidefinite. And if we summed over all j's, so from 1 up to n, we would just get the identity matrix. So this is kind of greater than 0, but less than I under the ordering that a is less than b if and only if b minus a is positive semidefinite. So hence we get the appropriate bound for the diagonal entries. Similarly, without this 1 over d term, this guy is closely related to a squared. So now if a is, or the graph is d regular, then the diagonal entries for a squared are just going to be d's. So this 1 over d term will ensure that the diagonal entries here are going to be at most 1. So by using the observation presented on the last slide, we conclude that the positive discrepancy is lower bounded by the sum of the non-negative eigenvalues. It's also lower bounded by some of the non-negative, some of the cubes of the non-negative eigenvalues divided by d. And by Cauchy-Schwarz, we can also get the appropriate bound involving the sum of the squares. So as we recall, for any graph, the sum of the squares of all eigenvalues is just nd. So if this sum contributed to that at least some positive constant proportion, we would get n times root d as a lower bound, which would be great, and it would be a random graph. Unfortunately, it could be the case that essentially the negative eigenvalues contribute all but a little over 1 proportion of the sum of the eigenvalues squared. So we have to do something else. So let's look at this matrix y, which is closely related to a squared. So essentially we pick a squared, which we know is positive semidefinite. Then we subtract an appropriate multiple of j, so that this now has eigenvalue 0 for the all-one vector, which is the same as saying that this new matrix will have some of its entries being 0. And then we scale it so that the diagonal entries are at most 1. Then what's the discrepancy of y going to be? By the same argument, it's going to be the sum of the eigenvalues cubed, except for the first one. Yeah, we should divide by d. But we also know that the sum of the eigenvalues cubed is the number of triangles times 6. So what we get is that this discrepancy of y is basically counting how much we deviate from the expected number of triangles. So there are some other arguments based on tools used by Benny, Oliver, and Stefan in their paper concerning MaxCut for page-free graphs, which adapts to our setting as well, which can be used to deal with those cases when the number of triangles is greater than the average, or if the number of triangles minus the average is small in absolute value. So loosely speaking, we can assume that this must be very small, so negative and very large in absolute value, or else we would be done by using these other methods. So basically, we can assume this matrix gives us large negative discrepancy. What does it mean that it has large negative discrepancy? So the discrepancy of y is defined as this inner product, but because the inner product between y and j is just 0 because we have killed the all one vector, this discrepancy is just going to be the sum of the entries in the Hadamard product of y and a, which means that the terms of y corresponding to the edges of g must be sort of heavily negative. So, but we would like to make them positive. So one way to make them positive is to consider the Hadamard product of y with itself. A convenient property of a Hadamard product is that a Hadamard product of two positive semidefinite matrices is still positive semidefinite matrices. Also, if they have diagonal entries at most 1, then the diagonal entries of the Hadamard product are also going to be at most 1. So this would be a great thing to consider. Unfortunately, this seems to be a bit too hard to control. Logically speaking, we are taking the sum of the squares here. So, but now it's no longer the case that the sum of the entries here would be 0. I mean, every entry is positive here because we have squared each entry. So it could be that essentially the negative entries would be sort of negative but small in absolute values, while the positive entries would be, there would be only a few of them, but they would be large. So when we squared everything, the sum would be huge and dominated by the positive entries. That kind of messes up things. So the squaring of entries is kind of too skewed way of doing. So we would like a smoother way of ensuring that we can flip those negative entries to positive ones. So minus a would be a great candidate of a matrix. Unfortunately, that's not positive semi-definite. So instead, we choose an appropriate scale version of minus a, and then we have to add I to ensure that this becomes positive semi-definite. So for this matrix, which is the all one, so the identity matrix minus 1 over t times a, and then we add a suitable multiple of j to cancel the sum. It's true that for any matrix R, the discrepancy is sum of the diagonal entries, which is small, minus the inner product of R and A, which is essentially the discrepancy. So for this matrix Y, we considered the discrepancy of the Hadamard product with Z is going to be minus 1 over t times the discrepancy of Y. So we flipped negative discrepancy into a positive discrepancy. Now, of course, the question is that how do we choose our t? Well, the diagonal entries must be at most 1, and that gives us a condition that t must be at least root d, and we would like to choose t to be as small as possible. However, the positive semi-definiteness condition implies that we should choose t to be at most lambda 2. And this is quite funny because here sort of large second eigenvalue is hurting us. That kind of explains why we get better bound for the second large eigenvalue, because here it's not really the case that small second eigenvalue would be hurting us, but it's really the case that large second eigenvalue is bad for us, which is kind of counterintuitive. But to get around with this, we just pretend that it's not a problem. And we add an error term, which is essentially taking care of those things. So looking back here, this matrix on the top line, we could just write it as lambda I times vi transpose. So, and here we have vi transpose. So what we are concerned with is those eigenvalues for which 1 minus lambda I divided by t is negative. And to compensate, we just add this lambda I over t to force those terms to be positive for those eigenvalues which are too large. That would make negative. And then we would hope that the contribution for the discrepancy arising from here is small, substantially smaller than the discrepancy of Z. And to do that, we would need to bound these two quantities. And because I think I'm running out of time, I'll just skip the rest of the details. And as a final thing, I'll say a word about what happens for when the graph is has average degree near half. So in this case, a construction of the kern, which was used to prove that there exists a graph with order d squared equiangular lines, has positive discrepancy of the order n to the 5 over 4, which is like smaller than the lower bound we had for the second eigenvalue and matches with the lower bound we had for the positive discrepancy. So at least for the second eigenvalue, there has to be a new phase transition. And this suggests that maybe for the positive discrepancy, something else should occur for graphs which have density at least half and which are still far away from theorem graphs. And essentially open questions that can we close these gaps? So can we improve the upper and lower bound? We believe that for d less than half minus epsilon n, it should be d to the 1/3 n, but neither the lower or upper bound matches with it. And for higher densities, 5 over 4 could be the right exponent. It is a lower bound for strongly regular graphs. We can prove that, but in general, we have no idea how to proceed. Well, and that's all I wanted to say. So thank you very much for the opportunity to speak, and sorry for rushing a bit the end.
Thank you so much, Eero.